As you said, I'm Bryan Fink, I work at Basho, and we're going to talk about some Riak Pipe. So what is Riak Pipe is probably your first question. And what it is an abstraction on top of Riak Core. And if you don't know what Riak Core is, I'll go over the important parts in just a minute. But the abstraction it provides is one of staged computing. So you might be familiar with the fetch and render sort of application flow. So you get a request comes in, you have to look up something in the database, you have to render it into something that the client's going to want. Lots of applications do this, just the process that picks up the socket, that takes the client request, grabs the thing from the database, and does the render itself. But there's an alternate way to do it, which is to set up processes, one process for doing the fetch from the database, and one process for doing the render. Why did we create Riak Pipe is your next question. And we'll come back to why it's structured the way it is after this. Riak Pipe is the thing that powers our MapReduce thing in our query system in Riak KV. Riak KV's MapReduce is a staged computing system. It's a query system that allows you to express a query in stages of two types. One is a map type, which is very much like the functional map. It takes inputs that are keys into a database and applies a transform to the value that is associated with each of those keys, and passes that on to whatever stage is next. Reduce type stages aggregate whatever came in from the stages ahead of them and produce one unique output from all of the funneling that came into it. And Riak's MapReduce is a very old thing that has grown in fits and spurts as we've needed things in it. It started out as something that we called link walking, if you're familiar with Riak, which was a way to express sort of relations between keys and values in Riak. So you could say that a person owns these documents, and these documents came from these sources, and then instead of having to query sources for who created them, you could say, I want to look at sources from a user by saying, we're going to start at this user object and follow all the links to all of his documents and all of the links to all of those document sources. The problem with that sort of slowly growing and aggregating feature set is that it ended up basically a mess of Erlang processes that we just fired messages off everywhere to say, go get this thing and do this thing to it and whatever. So we needed a much more clean abstraction such that we could debug things, we could monitor things, and especially so we could provide back pressure. Mahesh gave a great introduction. That was fantastic. And if you were here for it, you'll see a lot of those topics come up. But one of the problems with Erlang processes is that their mailbox is very much like a queue, an unbounded queue. So if you have processes that are consuming inputs very slowly, but receiving inputs very fast, their mailbox grows and grows and grows and grows until your Erlang node falls over. So this is the conceptual problem. With all of these processes that we had going on, we were just spawning processes everywhere. We had no control over how many of these processes were spawned at any time. We had no control over how big their mailboxes got. And because their mailboxes were getting so big, we had no control over how long it might take some input to make it all the way through the system. And like Mahesh said, if your queue is getting longer and longer and longer, the time for any one input to get all the way through the queue is getting longer and longer and longer. So we started looking for a solution, and we happened upon a paper that came out over 10 years ago by the name of Staged Event-Driven Architecture. This is a really great, simple solution that is this sort of staged processing. So it consists of two pieces. After you've got this stage set up that you're doing little pieces of whatever it is you're trying to do independently, you set up a queue for each stage. So you send the input to the queue, and then you set up a thread pool that consumes elements from the queue. What this allows you to do is tune in very two simple parameters how fast things are moving through the queue and how parallel that can be and what the maximum latency is, because you can tune how large those queues are allowed to grow. If you have control over the queue instead of the Erlang mailbox, you can say, I know there are too many things in here. I should drop things on the floor, or I should tell things that are producing my inputs to slow down. And you can change the size of that worker pool, consuming inputs out of that queue. So you can say, I have bandwidth. I may as well consume more things to get them through faster. Or you can say, I have this thing that is under high contention, so I should have fewer workers, so they're not all trying to gather it. I'm sorry, all trying to use it at the same time. What Riak Pipe does is apply this SATA architecture to Riak Core. I said I'd explain Riak Core. What Riak Core is a way to model distributing work across a set of nodes, a set of computers. The way Riak Core does this is to define a hash space. We happen to use 160 bits. We break the hash space up into segments. So there's one segment from 0 to 1 million and another segment from 1 million to 2 million. Obviously much larger numbers because we're dealing with 160 bits. And then each of those partitions we give to one of the nodes in the cluster. So there is some node that is responsible for handling anything to do with that partition. When Riak Pipe gets an input, or when Riak KV gets a key and value, Riak KV also operates on Riak Core, we hash that key or that input. Wherever the hash lands in the hash space, we send the input to the node that is responsible for that partition. It makes it really simple to add more nodes and just have them take over some partitions instead of having to negotiate that, okay, now you have from A to B and that kind of thing. And the consistent part of consistent hashing is just that, especially in Riak KV, we're hashing on the key instead of the value. The key's never going to change. So even when the value changes, it's on the same node, or it's at least on the same partition. And if we've changed which nodes own that, we're still going to the right node, that kind of thing. So, like I said, Riak Pipe is on top of Riak Core. The way Riak Core applications work is for each partition, a node spits up an Erlang process. That Erlang process is what you're sending the input to. So you figure out which partition it's going to, which node owns that partition, and then you send it to the process on that node owning that partition. Riak Pipe puts the SATA queues and the SATA workers connected to that, we call it a vnode. It's a virtual node that owns that partition. The vnode is responsible for managing the queues that that stage is receiving inputs into. It's also responsible for starting the workers to consume those queues. So when we send our input to the partition, it looks up which queue, we tag the input, with what stage it's for. It looks up the queue for that stage, puts the input into the queue, and starts a worker if there's no worker ready for that queue. And the worker eventually consumes things from the queue, and we'll go into how that works in a little bit. But what this means is that if we think about it as each stage is a different queue in the ring, we kind of we can define this stage of processing, that fetch and that render and whatever, or the map and the reduce, and we can route around the cluster. We can send an input in, and it will go to the partition that's supposed to handle that input. The output that that stage produces is the input for the next stage. So we can route that input to whatever partition is supposed to own it for the next stage, where the next worker lives, and so on and so forth. But I don't mean to say that each stage operates on only one partition. We're not going to send all of the inputs for that stage to a single partition necessarily. In fact, the way we define the thread pool is by that exact hash of the input. So if the inputs are not all sent to the same partitions, then we have different workers on different partitions doing work for that same stage. So we could in fact route all of the inputs for the first stage to one partition and use a different hash on that on the outputs of that partition. I'm sorry, on the outputs of that stage to route to different partitions for the next stage. So on and so forth. We can aggregate again later down the line. And that hash function, like I say, is exactly what defines how parallel, or how many worker threads are working on the inputs for this stage. So I'm going to go through a few hash functions and how they apply right now to get kind of the idea for it. The simple one is just to hash with an SHA hash. All that's going to do is spread inputs all over the cluster. SHA has a very good spread. An input that is just slightly off of some other input will end up somewhere completely different in the cluster. This is great if what you're trying to do is just get as many workers working on things as possible. With this kind of nice spread hash, you'll basically light up the entire cluster. So however many partitions you have going will be how many workers you have working for that stage. The other reason we use the SHA hash quite often for Riak Pipe inputs is Riak Pipe is often running next to Riak KV. Riak KV is also using the SHA hash to define where values are stored for keys. So if the inputs to our pipe stage are keys for Riak KV, then we send that input to the same node where the data is stored for that key. That means if our stage is doing a read from Riak KV, it's a local read. We don't have to take the value of that key across the network. So in addition to defining how parallel our system is working, we also define data locality. And we can reduce network load by making as much stuff happen local to the data as possible. This is kind of the basic idea behind MapReduce. That's why the system kind of works this way. But the other side is reduce. So sometimes you need all inputs to go to the same worker, such that that worker can decide something about the set of inputs instead of each input. To do that, you could still use an SHA hash, but hash on something that you know is going to be common between the inputs. For example, if these were bucket and key tuples, we might hash on the bucket, and we would get all keys for that bucket in one worker. We might use this to sort or to slice to find the top n keys, or some bit of data like that. Or we might just use it such that we only have one worker going. There might be something that we really just want a singleton on. You can also bin results. So slightly different. If you're hashing on something that is common to a few inputs but uncommon to others, you can sort of separate inputs. So for instance, if we're hashing on the first letter of some string, we'll get all inputs that start with O at one worker, and all inputs that start with T at another worker. This is somewhat like the classic MapReduce shuffle phase. So you could do kind of this keyed reduce where you would find the top n of the T strings and the top n of the O strings or something like that. This is not how Riak KV does its reduce. In fact, Riak KV takes the very shortcut and picks a random hash at the start for reduce. So we send all inputs to one worker such that you can do some total aggregation over all of the results at that reduce stage. One other interesting kind of one still exploits data locality, and we call it follow. So what follow says is, if you have two stages in a row, you say that the second stage is a follow stage. That means that any outputs that workers in the first stage produce stay local on the node where they were produced for the next stage. This one comes in really handy for reduce, and I'll show why a little bit later, but computing how follow would work from input to input is so difficult. You have to know where you're operating and sort of kind of, fudge the hash such that it looks like it's on the same node you're on, that we just created this nice shortcut for it that just says follow. It's just the atom. And I'll show where that goes in the next slide, as a matter of fact. I can see people are kind of glazing over, so I'm going to show some code that demonstrates how it works, such that you can get kind of a tangible feel. I've discussed kind of the conceptual bit of it. Actually using it is a very tiny amount of code, so I hope this will kind of make things a little more concrete. This example, as a matter of fact, sets up a pipe, sends inputs to it, gets outputs from it, and this is all the code that is necessary for it, except for the modules that are named, but I'm going to show those on the next slide anyway. They're very small. So if we can step through this real quick, you can see it's kind of 3 stages. The first stage defines the pipe, the pipeline, and each stage, I called it a fitting. I got a little, overboard with the pipes and the pieces that fit the pipes together. So each stage is called a fitting. And the thing you'll notice first is that C hash fun. That's that thing that I've been talking about how we hash the inputs. So you can see that, this is a fetch and render stage, and the first one is using the C hash fun that Riak KV is using. So we're going to send inputs to this stage that are keys for our key value store. And it's going to get the values of those keys for us. The second stage is the render stage, and you can see we're using the C hash fun follow. There's no reason for us to take all of those values somewhere else to do the render. We'll just do the render on the nodes where the values are. Some other things to notice are the module definitions. That's going to tell Riak Pipe how this fitting operates, what this stage does. And this arg in the second one is just a static arg that will pass to the init for the worker. So we've defined 2 stages in a nice list. All we have to do to start the pipe is tell Riak Pipe that this is a pipe we're going to use. This is kind of like creating an ets table. It's going to go create some metadata somewhere and give back a handle to the pipe that we'll use to send inputs to the pipe. So the second big chunk here is just sending inputs. You'll notice that we don't have to do any hashing. We just send it the input and the pipe that it's going to. Riak Pipe handles all of that hashing stuff and figuring out which node to send to, which partition on that node, where that PID is, all that kind of stuff. We just say, here's the input, send it to that pipe, please. This is just sending 3 inputs, real simple. The last bit of that section says EOI. That stands for end of inputs. So a pipe can stay up for as long as you need it to stay up. But sometimes it's useful to say, I'm not going to send this pipe any more inputs, like I'm done. And that allows it allows pipe to shut down workers. So, along the lines of, load regulation and whatnot, I said that we had the problem where we were spawning too many workers in our MapReduce. Riak Pipe has a limit on the number of workers that it will spawn, such that if you try to start up a pipe with, too many workers, it will say, no, this is not okay. Please go away. Come back later. I'm not going to allow you to overload the system. End of inputs allows Riak Pipe to say, there are no more inputs going to this worker. As soon as it is consumed all of its queue, go ahead and shut down the worker. That allows other pipes to start up later. Some workers even will wait until the end of inputs to know that it's seen everything it's going to see before it sends outputs down the line. That's what our reduce phase uses. But that's all that is. It's just informing the pipe that you can shut down when you're done. And the final stage is just collecting the outputs. We could have, in the spec up above, told that second stage to send to some specific PID somewhere or even some other pipe somewhere. Since we didn't tell it, it's just going to send outputs back to the process that started the pipe. And that's all collect outputs is going to do, is look through the mailbox and find all of the pipe output messages and hand them back to us. The tuple that it's returning is saying that I did actually get an end of inputs and all of these outputs. So we'll talk about the render stage and how to implement that module, because the Riak KV pipe get stage does some special stuff for KV, because KV has a lot of nooks and crannies. But this is the basic form for any worker. All it needs is 3 functions, init, process, and done. Init is called as soon as a worker is started. We give it that arg and say, create any state you need to. Some things open files that they'll keep open for the life of the worker, or some things, do some pre-computation so they don't have to do it on processing. Process is called for every input. So when an input arrives in the queue, we wait around, and as soon as it's ready to come out of the queue, we call process on that input. And process is where the stage does what it's going to do. Process is completely open. Do whatever you're going to do. This one happens to call the mod and fun that we passed in the argument to the stage. The Riak KV one goes and talks to a Riak KV vnode to pull out the value for a key. It is also the stage's responsibility to decide when it's going to send outputs. This is not a functional thing. It's not, hey, process, give me the outputs that you're going to pass on. This is, you're the stage, decide when you're going to send outputs. So sending outputs is as simple as sending inputs. We just call the send output function with the fitting details. The details we passed in the init also include a handle to the next stage, so all of that hashing is done automatically again. And the final function that a fitting needs to implement is just done. So as soon as done returns, we know we can shut down the worker. So done could send more outputs, or it could close files, or anything like that. But the important thing is you're about to shut down, finish up. And this is just what that module and function might look like that we passed into that generic worker. This is just, render. So it's really simple code to write, actually. You don't have to do any of that hashing and whatnot. It's mostly, at this point, just thinking about how you want to distribute that workload across the cluster. And to help you think about that, I want to go through specifically what Riak KV does in a MapReduce query. So if you send a very generic MapReduce query, it has one map stage, one reduce stage, we translate that into 3 Riak Pipe fittings. The first fitting gets values from the key value store. The second fitting applies a transform function to that value. And the third fitting does the reduce. So we take all of the values that were produced from the transform and aggregate them in some way. This particular definition is actually used in React CS. We use MapReduce to compute how many bytes and how many files each user is storing in our React Cloud Storage, our S3 compatible system. So we send in all of the keys in a bucket, and it goes and looks up the file metadata for each of those keys and pulls out the size of the file and the fact that it is a file. And sends it on to the reduce. And the reduce, you can't see it in this function that just happened to be how Erlang printed it out, but it's basically, count up the number of instances you got and sum the bytes. Very simple. But you can see, the hash function we've talked about. The first one is using that Riak KV hash function to do the local read. The second one is using a follow function to do the transform locally, so we don't have to send all of those file metadatas all the way across the network. And the last one is using a constant such that we can do the sum and have the total sum instead of having to send all of those results to the client. You can also see in here that I've actually specified the queue limit. I believe this actually is the default queue limit that's used, but it can be useful to say, this queue is allowed to have more space, especially in the reduce. We can up the queue limit and allow the queue to grow and have the reduce run just every once in a while kind of thing. But that is how we tune the, whether work is being dropped on the floor. Actually, some of what Riak Pipe does is instead of dropping work on the floor, we do actually say to the upstream worker, please hold on for a minute. Don't send me anything more. Whenever a worker sends an output, it's waiting for a response saying, okay, it's fine to send me more. And I know that's the bad idea, the tail drop that Mahesh just talked about, but this is sort of the first idea. We're actually experimenting right now with ways to do that better, so we'll be looking into Red and Codel and all that kind of stuff. But the interesting thing about this practical example, and kind of the aha moment about how C hash funds can apply, is, like I say, we're using this for React CS. What we can do is we can duplicate that final reduce fitting and actually use it twice. But the first time we'll use a follow function, a follow hash function. The second time we'll use the constant. What that means is we'll actually run that same reduce function locally on the nodes where the transform is happening. So we can do several sums and then send them to one final place for a total sum. Visually, this kind of looks like this. So the top one is our three-stage get, map, reduce, or get, transform, reduce. And we keep things local. That's what's showing in that first stage. And then the second transition is the funnel down to one partition. The second one with the for looks like I've just complicated things. You know, I have more arrows going on. There's another stage in there. The funnel is narrower, that kind of thing. The interesting thing about this is realizing where the node boundary is. So I said I've been keeping this data local. The node boundary is across that funnel. So if we're computing storage for someone that has millions of files, that transform stage would have sent millions of file metadata, or that simple one with the size of the file, to that reduce stage. With that follow reduce stage in there, do all of that locally on each node, and then send a constant number of messages across the network to that final reduce stage. So in a standard Riak setup, we're using 64 partitions. In that setup, we would send 64 messages instead of millions of messages across the network to the reduce stage. This is incredibly effective. You get to do that parallel sum before doing a very small sum. Using this, we can compute the storage that each user is using in like half the time that we did before. And there's some other optimizations that we'll probably throw in. But that alone, just duplicating that stage and using a different hash function was kind of the aha moment that this was probably right. So I've talked a lot about MapReduce. I do that because this is the practical thing. This is what we already have built. I can actually say, this is code you can go read. I can say, this is how it works. But people want to know about other apps they might build with this, because it's not just MapReduce. It's a general staged computing system. And I think it's a pretty wide range. I think almost anything you could build on React Core, you could build on Riak Pipe. If what you're doing is talking to partitions saying, hey, give me this thing, probably makes sense to talk to just React Core. If what you're doing is something that has several steps to it, it might make sense to use Riak Pipe, such that you don't have things being overwhelmed. You don't have unhandled parallel amounts of work, that kind of thing. I actually think we could even do parts of React KV, our key value store, as a Riak Pipe app. If you know anything about React KV, you know that the get stage is sort of the get operation is sort of several stages. We actually fetch several replicas of the data from different places around the cluster, and then we reconcile those pieces of data. So we say, which one's the latest, which one's the most up to date, and then any of them that were out of date, we go and talk to those nodes again and repair that data. This is a pretty obvious 3 stages of things. I think we could do this as a pipe app, and that might help us with making sure that all of the work we're doing to reconcile things isn't causing slowdowns to clients because they can't fetch things and that kind of thing. We'd be able to tune how much reconciling is going on at any one time, or how much fetching is going on at any one time. Same kind of thing with put. Other apps I'm not sure about. I get a lot of questions about. Someone just wrote a demo app that does, it fetches items from Reddit. So it looks at a subreddit and grabs all the URLs and grabs all the content from them. I think his name is Eric Moritz, and he open sourced it on GitHub. It's called Riak_pipe test or something. And it sets up an entire cluster with pipe and code to go, so that might be something to look at. But yeah, I think anything stage computing that you want to distribute might be a possibility. Current things that I'm working on Riak Pipe, honestly, is mostly about making MapReduce better, because our MapReduce system is something that people want to use more and more, and making it better and better would be a great thing. But specifically, I already alluded to Mahesh's talk several times, but that interworker messaging efficiency is something we want to work on. The back pressure, the simple, it's a tail drop system, like he said. We put back pressure immediately on every message, or we drop messages immediately as soon as the queue gets full. And that was needed simply because we transitioned from a system where it was just Erlang processes, and blowing up those message boxes, mailboxes, was taking the system down. So even just getting to tail drop was a giant leap forward for us. I know this is an Erlang conference, so everyone is happy to write in Erlang to get this thing working, but other people do want to have stages that are defined in other languages, especially Java. There is a boatload of text analytics and image processing and whatnot in Java. There's a boatload of scientific mathematics in Python and C. People would love to write fittings in those. So we're working on ways to get out to that. We'd like something general, so we don't have to implement it over and over again. It might be some simple TCP connection or some simple Erlang port. Hopefully that will work out. By the same token, right now you have to be on a Riak node to start up a pipe and to send inputs and whatnot. So we're looking into an external interface, probably something protocol buffer shaped, where you connect and then you have messages that you can send back and forth to get inputs in, get outputs out. Still up in the air. Long-running pipelines is another thing. I said you don't have to send end of inputs, and I said that it's just setting up metadata like an ets table, but kind of like an ets table, if the node that you started a pipe on goes down, the whole pipe goes down, because those metadata processes are only on that node. So we're working on stuff to do that. Something that will, a distributed FSM or something. If you've been catching up on distributed papers, there's a new one called Raft that does distributed finite state machines that are reliable and can tolerate failures and stuff. So something like that might be able to keep pipelines up across node failures. So we think that'd be pretty cool. But other than that, I think that's about all I have to share with you. If you want to know more, all the code is on GitHub, and in that GitHub repo, GitHub basho Riak Pipe, there's also a README that goes into all of the supervision trees that are doing this, all of the message formats, all of that kind of thing. So there's lots of data there. We also published a paper at the CUFP last year, and if you have an ACM membership, you can go look up, the paper is titled Distributed Processing, something about Dynamo, something about Riak Pipe. Sorry, it's a long thing that they talked me into. If you don't have an ACM membership, you can go to my page, beerright.com/brian.html, and scroll down until you see that little ACM rectangle, and it's a link to a free copy of the paper that the ACM will give you. I'm hobbyist on Twitter, so if you want to throw tomatoes at me, go nuts. The slides I also tweeted just before this talk, so if you would like to go back and review those, they're up there. You can always find the Basho team on Twitter. But that's all I have, so I'm happy to take questions if there are any. The inputs are Erlang messages, so it's across distributed Erlang right now. I'm sorry, what was the first word? SSL listener. So in the Riak KV's MapReduce, it provides the interface to submit those queries on HTTP and protocol buffers. And part of those queries include an input spec. And that input spec can either be a list of keys or a command to go find all the keys somewhere. And that's how we generate inputs right now, is either just by iterating through that list or sending off some worker to generate a list to iterate through. But no, there's no generic TCP input right now.
I have a question.
Yeah, please.
I forgot how to correctly phrase that in English. How resource intensive is starting a Riak pipe?
It's starting a
So
Riak pipe.
how, I mean, can you sort of just fire them up and shut them down like thousands a second or something?
Right.
Or not?
So firing up a Riak pipe is kind of a two-stage process. The first thing is just that execute that tells Riak pipe that this is my definition. That is a handful of supervisor calls. So we heard Joe say that supervisor startup is slow. So yeah, that's some number of milliseconds. The second stage of it is Riak pipe doesn't actually start up workers until a vnode receives an input for a stage. So your first inputs for each stage will require a little extra startup time to get that Erlang process started. But then other inputs are just, consume the queue. So I don't have numbers like on me at the moment. But yes, there is a startup cost. Shutdown is a little bit lighter because it's just, any vnode that I know is already running a worker, just send it the message. It does have to wait to synchronize and then send it on to the next one such that we know, because any worker can send any other worker a message. So we do have to wait until one stage shuts down before we start shutting down the next stage. So as far as time to start up and shut down, those are actually, kind of big things to get across. So longer running pipes will be more efficient than shorter running pipes. Okay? Yep. Excellent. You said you had a question.
He called it.
Oh, excellent. Fantastic.
Anyone else? Thank you. Thank you, Bryan.
Thank you.